Alright, so this is a presentation about operational amplifiers, and you will be happy to know that this is the last presentation. So operational amplifiers is, this is the schematic symbol of it, and we'll talk about what these terminals are and things like that. It's probably one of the most common electronic devices that you will see as far as an active device goes. Most common electronic devices probably are being resistors. So operational amplifiers, they have a couple of characteristics. Is that they have very high gain and they have differential inputs. So what that means is these two inputs, those are the differential inputs. So you notice that there is a minus and a plus. That's those two inputs. And what's unique about this device is it has actually 4 inputs. So we have so far talked about devices which have 1 input and 1 output. So this thing actually has technically 4 inputs. It has this negative one, this positive one. This one is called the inverting input. This is called the non-inverting input. And this is the plus voltage supply, and this is the minus voltage supply. So this is like if you take a digital, you remember the VCC and ground. Okay. So these are the differential inputs, as I said, and this is the plus and minus voltages. Okay, so these two are, as I said, are the plus and minus voltage supplies, and this is the output. So, differential inputs, plus voltage, minus voltage, and the output. Okay, and they come in different sizes, shapes. So this DIP, that stands for dual inline package. So that means it's 2 packages like that. They're in line like this. And this is pin number 1, and you know that it's pin number 1 because it's right next to this notch or this dot. This is the one. So these are surface mount devices. That's SMT, surface mount technology. Okay. Some of them have 8 pins, some of them have less, some of them have more pins. So it just depends on what the packaging is. You'll have to look at the schematic and look at the manufacturer's specifications to know what each of those pins mean. Okay, so we talked about the inputs, which is these two, and I mentioned that this is the inverting input and this is the non-inverting input. So that's because of the negative here. And it has 1 output. So if you look at an ideal op amp, it's like, remember when we talked about ideal diodes or something, where you had a straight line happening at the moment you forward biased it. Or if you looked at ideal bipolar transistor or ideal field effect transistor. So there's a model that we look at ideal operational amplifier. Okay. So we use that just to make sure that we have to simplify the analysis. So they have an infinite gain, and remember we talk about voltages here, and the bandwidth of it is infinite. So again, these are just ideal concepts. Obviously enough, you can't have infinite bandwidth. Okay. And input impedance is infinite, and why this is important is why. I'll let you think about that for a second. Well, the importance is that if you don't have a high input impedance, then what happens is the devices that are supplying the power to it are also powering this operational amplifier. And you don't want to do that, because what that does is load down the devices upstream. You don't want to load up the devices upstream. You want to have the power internal to the operational amplifier to take the intelligence of the information coming and amplify it. And zero output impedance, why that is important, is the opposite of this one. And why is that important? Why it is important is that if you don't have zero output impedance, that means the device itself has high impedance, which means the power dissipation of the device is high. So the power gets dissipated inside the device. You don't want that happening, because that means your circuits are going to get hotter and hotter. Eventually they'll catch on fire. So that's why this characteristic is important. So all of the amplification goes to the output without any impedance. Obviously, impedance is the same thing as resistance, but it's factoring in frequency. So if we're talking about this device, that means whatever device that's supplying the power to this does not have to have actual power. It just has to have the intelligence being supplied to it. And then when the information has been processed inside this device, all of that information gets sent to the output without anything getting dissipated in here. So that's why this output impedance, the characteristics of these two are important. Bandwidth, if you limit the bandwidth, then the frequencies that it can react to or it can work with get limited. And infinite voltage gain means that it has very high voltage gain or amplification. Okay. So it has these characteristics. And so if you look at the block diagram, it is these devices essentially that are incorporated into one chip or one integrated circuit. And that's essentially a operational amplifier. And obviously we are not going to follow through this, but you should be comfortable with all of these devices and how they are working and the functionality of them. And if you look at these blocks, that's these blocks right here. So this is a typical schematic of an operational amplifier. So what's interesting about this is that if this non-inverting input is bigger than this inverting input, the output swings to this voltage. Let me repeat that. If this number here is bigger than this number here, then the output swings to this. If this number is bigger than this number, the output swings to this number. So that's kind of unique, because that's not what we've talked about with other devices before this. The other devices, this output has been dependent on these inputs, the absolute numbers of these inputs. Now we're talking about the difference of these two. So again, if this number, let's say 5 volts, and this is 4 volts, the output will equal this one. If this is 5 volts and this is 4 volts, the output will equal this one. So the output, let's say this is connected to 15 volts and minus 15 volts. If this is 5 volts and this is 4 volts, this will equal minus 15 volts. And if this is 5 volts and this is 4 volts, this will equal 15 volts. It won't equal the difference between these two. It will equal this number or this number. So that's like a differential amplifier. There are some other schematics of this that we use this as a linear device, but as far as a digital device, that's this one equals this number or this number. It's not equal to these numbers. I wouldn't say it has nothing to do with them, but it just looks at the difference. So what if this number and this number is equal to 0? What will happen to this? Obviously it won't go to 0. Because, like if you say this is 5 volts and this is 5 volts, it's almost impossible to get 5.000, and same thing here. You can come very close to those two numbers. And what happens with those two numbers is, if this is say 5.0 and this is 5.001, then it will come close to this number. But let's say you do not want that to happen. So that's the offset that you apply to one of these to make sure that these two are equal to 0. And that's the input offset voltage. So if you look at the amplification of these two, you'll see this output. So another feature that we use with this is feedback. So this is talking about negative feedback. Remember I said that they have an infinite amplification. Sometimes you don't want that. You want to limit that amplification because you don't want this to be too high. And then you can change that by having this negative feedback loop. So part of this output gets fed back into the inverting input, which kind of reduces the amplitude of this number here. So here's a circuit with negative feedback. So you have this output here coming through this 100K resistor, feeding back to this input here. So with op amps, generally these numbers are the same. Like the non-inverting is 2 and the inverting is, the non-inverting is 3 and the inverting is 2. Positive supply is 7, like that. But you really need to look at the schematic to make sure that they are correct. I mean, it doesn't have to be. Most of the time these numbers are correct for a 741 series operational amplifier. This is the most common number of these, by the way, 741. Okay. And we are feeding it to these two in 12 volts, plus 12 volts and minus 12 volts. So can you just imagine if this number, this 2, input is bigger than this number, the output will go to negative 12 volts. If this 3 is bigger than 2, then the output will go to plus 12 volts. So in this case, we are feeding back some of this into this so that the numbers will become closer than plus minus or minus 12 volts. So if you want to get some number amplification which is between these two numbers, that's when we have this feedback cycle. And that's the formula for calculating the gain of this particular amplifier with the negative feedback loop. So this is a non-inverting amplification circuit, and it's this formula. So the closed loop gain is the gain, and Ni is the non-inverting. 1 plus Rf is the feedback resistor, which is this resistor, and that's the input resistor, which is this number here, 10K. So with those numbers, the gain of this amplifier is 11. So in this case, we are inverting this, we are grounding this non-inverting input. And we are applying the the signal through the inverting input. So we have output which is inverted. And the formula for calculating that in closed loop, so I is standing for inverting, negative, so negative number means because it's a negative amplification, this feedback resistor, which is this one, Ri is this one here. So I'll go through an example with some actual numbers and you can follow that through. And a multisim, I have all of these developed, and I'm going to make that a different lesson because I can't click on the computer while on the PowerPoint. So we'll keep that separate, and I'll come back to the multisim circuits in just with the next video. It spelled analog funny, didn't they? So comparator circuits means it just compares these two numbers. So this is a reference number, and then this is the actual information data coming through. It compares these two numbers and produces an output. And that's why it's called a comparator circuit. So if the input voltage is greater than the reference voltage, then the output voltage will be plus VCC. So what I'm saying is, if this number is greater than this number, the output will become this number. And if this number is smaller than this number, then the output will become this number, minus VCC. Okay. So we'll build these circuits in a little while. Here's an actual application of that comparator circuit. This is like a smoke detectors. This is how smoke detectors work actually. So you have these LEDs, and so they'll either turn this one on or this one on. And then it goes through this circuit and produces an output. So if smoke enters this region, what happens is that this LED will shut off. And here's another circuit that is used for an irrigation circuit. What it does, it measures a set value of soil moisture to the actual moisture reading from a sensor, and either can produce an output or not, and that automatically irrigates the soil. This is another circuit using a temperature control system, and so it either will energize this relay coil or not. So here's a classic op-amp comparator circuit. So what happens is, when this number, this non-inverting input, is greater than the inverting input, the output will become positive. So if this one is, let's say, 5 volts and this is 4 volts, well, I can go actual numbers for that matter. It says 1.3, right? So this is 1.3 volts. So if this is, let's say, 2 volts, for example, okay, then this number is bigger than this number comes down to here, goes to here, and goes to this NPN transistor, which turns this transistor on, which turns this light on. So what that means is, when the non-inverting input is bigger than the inverting input, this LED comes on. So if this is, let's say, 1 volt, or let's say 0.5 volts, or connected to ground for that matter, or 0, then this number is bigger than this number here, right? So the inverting input is greater, so this number becomes the negative input, and so this number is 0 volts here, or I'm sorry, negative 15 volts. It doesn't say that here, by the way, but if you just look at the battery, you can tell which one is negative. So that's negative 15 volts, so I'll have negative 15 volts. So you don't want to actually apply negative 15 volts to this base, and that's what this diode does. It takes that negative 15 volts and forward biases this diode to ground. So you'll have a path of current like this. That's if this negative number is 1.3 and this is 0. The other way around, then this plus 15 volts will come out here. This diode will be reverse biased, there won't be any conduction, it will go into here, and this LED will turn on. And so this is a comparator circuit, so you can see like different values here. What that does is it gives me the flexibility to see, like, if it goes up like here, when does that become greater than this number here. Also it gives me the flexibility of changing this and changing this number. So if you look like a gauge of some sort, that's how comparators work as far as gauges go, or even thermostats and things like that. And there's a formula for calculating that. The output voltage, we are going to just use a voltage divider formula for that, which is this voltage right here we're talking about. So input voltage in this case is this voltage 15 volts. R sub X is this resistance between these two. So if this is what, 3.5, so that's 7 kilo ohms, and then the total resistance of this whole network. So this is, you should be familiar with this voltage divider formula. So this, in this particular case, if I want a particular voltage, so what I'm trying to do is get 1.4 volts to become greater than this voltage. So I just plug those numbers in. 1.4 volts, 100K is the total resistance here, divided by the 15 volts, which is the source voltage right here. So it's 10K. So if this terminal was connected here, like this, can you tell me if this will be greater? If this non-inverting will be greater than the inverting or not? Right. So I hope you said that no, it won't be, and that's true, because this is 3.5 is 7 kilo ohms, so that's smaller than this number, right? So it needs to be greater than that. So if you went up to here, for sure this number will be greater than this number. Okay. So here's some from multisim itself, and we'll build this circuit on multisim. Well, you will build it, I already built it. Okay. So this is actually, if you're connecting the circuit to get plus and minus 15 volts, obviously we are not going to do that thanks to Mr. COVID virus. But if you actually build in this circuit, you need to have this plus and minus 15 volts for the circuit to work. And it's kind of a shame that we won't see that. But this, you require two DC power supplies. You know, most of the time we've been using just one power supply of the triple power supplies, or maybe two with the 5 volts. But this actually uses both of the major power supplies, not the 5 volts. So this is a configuration, and I've just explained it how it's done. So this actually gives the plus 15 volts, and this gives the minus 15 volts. And what you do is you short circuit the negative and the plus of power supply A and power supply B, and that's how we do it. And this gives the ground reference for the two. So between here and here I'll get plus 15 volts, from here to here I'll get minus 15 volts. So that's actually the rewiring of it. You see how I have connected it. So if you follow this yellowish color wire. So this plus actually is going into this minus here. And that's showing when an amplification or the differential amplifier working. And that's the actual circuit that I built. I know you're going to be very sad that you're not going to be building it, but that's that 741 LM741 operational amplifier. And this is the plus voltage rail, and this is the minus voltage rail. There's a common ground between the two. And how you get that is, you see how this switch is pulled out, and that what that does is it puts these two power supplies in series with each other. This is pulled series. I know we've never done that, but so this would have been experience for us. So that's connected with the two power supplies. And you notice how the voltages are just controlled by one, not the other. Because this is connected, you can see that it's actually at 0. You see how it's turned up. And this shows 21 volts peak to peak versus this one is 2 volts. And the frequency of the inputs will be the same. It's pretty close to 1 kilohertz. That's the actual signal that we are applying for the amplification. So we get 21 volts output from 2 volts input at 800 hertz. And that's actual chip. And here's that notch that I talked about. Well, the notch is here. The dot is here. And that's how I can tell which is pin number 1. Because for all practical purposes, you could take this notch and turn it around to here. That wouldn't tell you which is pin 1 then. So the notch and the dot will tell me which is pin number 1. So the other thing, of course, is it's typical that companies, manufacturers won't print the data of or the model number upside down. But the fact is that these could get erased and you won't be able to read any of these numbers. And then how would you know what's pin number 1? And that's a schematic. If you looked at this notch here, that's this notch here. And that's pin number 1. And these are the different inputs and the outputs. So this brings that negative 15 volts, positive 15 volts, there's no connection here, and the output is through this pin here. Offset null is what is used to make it equal 0 if you have to connect some kind of resistance value between these two if it's necessary to bring it to 0 volts. Alright, that's the end of the operational amplifier. We'll do the multi-sim experiments next.